Hello, this is Richard Hammack's Calculus 1 course. Today we begin part 4 of the course on applications of derivatives. This is lecture 30 on increase-decrease. Before beginning, let's pause to reflect on where we are in the course. Most recently in part 3, which was lectures 15 through 29, we learned about derivatives. The derivative of a function f of x is another function, f prime of x, which gives the slope of the tangent line to the graph of f of x at the point x. And in part 3, we learned lots of rules for computing derivatives. Beginning today, we'll start to put that knowledge to work with applications. The goal of lectures 30 through 34 is to understand the behavior of a function f of x, and in particular, to understand the shape of its graph. And our basic approach is going to be to use the derivative f prime of x as a tool to analyze f of x. And this is a little bit of the reverse of what we've been doing up until this point. In part 3, our primary object of study was f prime of x. That's what we were interested in finding. Beginning today, our primary object of study is going to be a function f of x. We'll compute its derivative and use it as a tool to answer questions about f of x. But then once we've answered those questions, we'll tend to forget about the derivative. It's done its job. The basic question that we'll be asking in lectures 30 through 34 is, what does the derivative f prime of x tell us about f of x? Today we'll see that f prime tells us where f increases and decreases. To illustrate that, consider the function that's graphed here. As you read from left to right, first it increases, and then, after that, f of x decreases as you read from left to right. Let's think about what's going on with, say, this part of the graph where f is decreasing. If you look at the tangent slopes at that part of the graph is going down, so all of those tangent slopes are negative. And if they're negative, the derivative f prime, which gives us the slope of the tangent, it's going to be negative. It's less than 0. And we'll tally that here by making a little row of negatives next to an f prime of x to indicate that for these values of x, f prime of x is negative because those tangent slopes are negative. But if we look at the part of the graph where f is increasing, as we read from left to right, those tangent slopes are positive. The graph is going up. So f prime of x, given the slope of those tangents, is going to be a positive number, and we'll indicate that by putting positives here, meaning that for these values of x, f prime of x is positive, and the slopes are positive, so the graph is increasing. The takeaway from this is that we can determine the increase or decrease of a function f as follows. F of x increases where its derivative is positive. So here's an f, it's increasing where its derivative is positive, and it's decreasing for a while. It increases again, those tangent slopes are positive there, so f prime is going to be positive. And f decreases where its derivative is negative. Here, and also here, f prime is negative, where that function is decreasing. So the takeaway is to find where f of x increases or decreases, look at the sign of f prime. Let's do some examples. In our first example, let's find the intervals on which the function f of x equals 2x cubed minus 3x squared plus 5 increases and decreases. So we know to solve that, we have to look at the derivative f prime of x, which is 6x squared minus 6x. In particular, we want to find out where that derivative, 6x squared minus 6x, is positive, which will be where the function f is increasing, and also where it's negative, which will be where the function f is decreasing. And if you look at that, what we're trying to do here is solve a couple of inequalities. Find out what makes this quantity positive or negative. And this is something that you've seen in pre-calculus courses. We know how to do it. One way to think about this is take that function f prime of x and factor it and look at the individual factors. F prime of x is 6x times x minus 1. And from that you can see that the derivative is 0 if either x equals 0 or x equals 1. So for those two values, 0 and 1, the derivative is neither positive nor negative, it's 0. So those are kind of special points, and let's plot them on the x-axis. Now we want to find the values of x that make f prime positive or negative. So what we can do is look at these two factors individually. Let's start with the 6x. The 6x, it's positive if x is greater than 0, and it's negative if x is less than 0. So we put positives and negatives on the number line here to indicate where this 6x is positive or negative. The other factor in f prime is x minus 1, and let's look at that separately. X minus 1 is positive as long as x is positive. As long as x is greater than 1, but if x is less than 1, x minus 1 is negative. So we put signs on the number line to indicate the sign of x minus 1. Now our derivative, f prime of x, is 6x times x minus 1, the product of these two factors. And let's take it interval by interval. On this first interval, 6x is positive, x minus 1 is positive, so their product is positive times positive. It's going to be positive. So f prime is positive on this rightmost interval. In the middle interval, 6x is positive and x minus 1 is negative, so their product is positive times negative, so f prime of x is negative on this middle interval. And finally, on the leftmost interval, f prime of x is a negative times a negative, and that's positive. So now we've figured out the intervals on which f prime is positive or negative, and we've got our answer. F increases where its derivative is positive. So that would be on the interval from negative infinity to 0, and also on the interval from 1 to infinity. And the function f decreases where its derivative is negative on the interval from 0 to 1. So there's our answer. And you'll notice that the answer does not even involve the derivative. Once we found it, the derivative has done its work, and we have an answer about the function f of x. Before we go on to the next example, although we're done with this one, I do want to say a quick word about what's happening here. If you graphed this function f of x, it would look something like this. It increases up until x equals 0, then it decreases until you get to x equals 1, and thereafter it increases again. It looks something like that. And these 2 points, 0 and 1, where it stops increasing or starts decreasing, or stops decreasing and starts increasing, the derivative is neither positive nor negative at those 2 points. It's in fact 0, as we noted up here. So where you have this switch from increase to decrease, or decrease to increase, you have 0 slope. You're at the top of the hill or bottom of a valley. And that's a point that we'll revisit later on. But for now, let's go to another example. Let's find the intervals on which f of x equals the cube root of x squared plus 1 increases and decreases. So we know for solution to find the derivative. And since we want to exploit the power rule here, let's make that radical a power. So we're ready to take the derivative of this function f of x. So we're looking at f of x equals x to the 2/3 plus 1. So its derivative by the power rule is f prime of x equals 2/3 x to the power of 2/3 minus 1 plus 0. The derivative of that 1 is 0. And that's 2/3 x to the power of minus 1/3. That simplifies to 2 over 3 x to the 1/3. Converting to a radical gives us 2 over 3 cube root of x. So that's f prime of x. And remember, we want to find where f increases or decreases. So we're looking for where this derivative is positive or negative. And for this particular derivative, that's really easy because if x is a positive number, its cube root is positive, so this whole fraction is going to be positive. But if x is negative, that cube root is negative, and the whole fraction is negative. So f prime of x, it's positive as long as x is positive, and it's negative as long as x is negative. So we've got our answer. The function f decreases on the interval from negative infinity to 0, and it increases where its derivative is positive on the interval from 0 to infinity. So again, once we've got that answer, it doesn't involve the derivative. We just use the derivative as a tool to analyze the behavior of f of x. Where the derivative was negative, f was decreasing. Where the derivative was positive, f was increasing. And that's our answer. We've solved this example. We've got an answer. But just as an aside, I want to take a look at the graph of this function f of x. Remember, that's the original function f of x. If you graphed it, it would look something like this. It would have a cusp right there. And on this side, it's decreasing. And then after that, it's increasing. But look at where it switches from decreasing to increasing. Something really special happens there. F prime of 0 is not defined. There's no tangent line at x equals 0. So we see in this example where f switches from increasing to decreasing, it happens at a x value with an undefined derivative. In our previous two examples, we saw that where a function changes from increasing to decreasing, or from decreasing to increasing, either the derivative is equal to 0 or it's undefined. And that's true in general. If f switches increase-decrease at a number x equals c, then either f prime of c is equal to 0 or f prime of c is undefined. If you think about it, if you're right at the point at which you're changing from increase to decrease, or decrease to increase, like here or here, the derivative can't be positive and it can't be negative because you're not increasing and you're not decreasing. So what could it be? If it's neither positive nor negative, then it's 0, or what's the other choice? If it's neither 0 nor positive nor negative, it's just not defined. So for instance, right here at this point, C, right there, where we change from decreasing to increasing, that happens at a cusp down at the bottom of that valley. F prime of C is not defined. And for this point, where we change from increasing to decreasing, right there at that C, f prime of C equals 0. And at this point, C, where you change from decreasing to increasing again, f prime of C is equal to 0. And right here, f prime of C is undefined at the top of that sharp hill. For other values of x other than these c's, the derivative is either positive, where the function's decreasing or increasing, or negative where the function f is decreasing. You can see from this picture that these numbers c, for which f prime of c equals 0, or f prime of c is undefined, are really special. And we give them a special name. A number c in the domain of a function, f, is called a critical point of f if either f prime of c equals 0 or f prime of c is undefined. So these four values of c that you see here, those are called critical points of the function f of x. When you change from increase to decrease, or decrease to increase, that happens at a critical point. And this leads to a process, a fail-safe process, for how to find the intervals on which a function f increases or decreases. The first thing you want to do is find all critical points of f, where f prime equals 0 or is undefined. And those critical points are going to divide the domain of f into intervals, as it did here. This interval, the next one, the one after it, and so on. So step 2 is to look at those intervals. And finally, the third thing you do is just check the sign of f prime of x on each of those intervals. Is it positive or negative? If it's negative, f is decreasing on that interval. If it's positive, f is increasing on that interval. That's essentially what we did in our first two examples, but here we're systematizing it and getting it down to a process. In our final example, let's use that process to find where the function f of x equals x plus the cube root of 3x minus 3 squared increases and where it decreases. Now, step 1 of our process is to find all the critical points of f. Those are the points, the values of c, for which f prime of c is 0 or for which f prime of c is undefined. And to find them, the first thing you have to do, in either case, is to find the derivative f prime and look at it. So we want the derivative of f, so let's write that as a power, so we'll be ready to use the power rule. F prime of x would be, let's see, the derivative of x is 1, and then we have 3x minus 3 to the power of 2/3. We have to use the generalized power rule for that. So that's 2/3 3x minus 3 to the power of 2/3 minus 1, which is negative 1/3, times the derivative of 3x minus 3, which is 3. The 3's cancel here and here. We can bring this negative power down to the bottom and then convert to a radical. So here is our f prime of x. It's 1 plus 2 over the cube root of 3x minus 3. Now we're looking for the critical points of f. The points at which the derivative is 0 or undefined. Let's look for where it's undefined first. Let's see, we have our cube root. You can take the cube root of any number, so that's not a problem. But watch out, you better not ever be dividing by 0. And when would that happen? Well, if x is equal to 1, because on the bottom you'd have 3 times 1 minus 3, which is 0, if x equals 1. So you can see from just looking at f prime that f prime of 1 is undefined because you're dividing by 0. And any other x could be plugged into f prime, but not 1. So there is our first critical point. X equals 1 is a critical point of f. That's the only point at which f prime is undefined. Now there may be some other critical points at which f prime is equal to 0. To find c for which f prime of c is equal to 0, how would you do that? Well, you'd simply solve the equation f prime of x equals 0. Find all the values x that make the derivative equal to 0. And I tell you what, we're going to do that off to the side here in a side computation. To find those critical points, we write down the equation f prime of x equals 0 and solve it. And f prime of x is this expression, so you have that equals to 0. You want to isolate the x, so get one of those terms with an x off to one side. Take that one over as its negative. And now we can multiply both sides by that cube root to get the cube root of 3x minus 3 equals negative 2. And remember, we want to isolate x. We're looking for what x would be. We need to get it by itself, so we could begin by cubing both sides to get rid of the cube root. That gives us 3x minus 3 equals negative 2 cubed, which is negative 8. Or 3x equals minus 5. And finally, to isolate the x equals negative 5/3. So what we've just figured out is that x equals negative 5/3 is the only value that makes the derivative equal to 0. So that's another one of our critical points. So we've completed step 1. We've found the critical points of this function. They are 1 and negative 5/3. 1 makes the derivative undefined, and negative 5/3 makes the derivative 0 when it's plugged in. Let's move on to step 2. And remember, step 2 was to divide the domain of the function f up into intervals based on the critical points. Now the domain of f, real quickly here, you could plug in any value of x to f. Its domain is all real numbers. So we take the entire line and put those 2 critical points in it, and that divides the line into 3 intervals. In step 3, we want to look at the sign of f prime on each of those intervals and find out where f is increasing or decreasing based on that sign. So let's start over here on the right when x is greater than 1. So you're in this rightmost interval. If x is greater than 1, let's see what's happening. F prime of x would be 1 plus 2 over cube root of 3x minus 3. If x is greater than 1, 3x minus 3 is positive, so the cube root is positive. So 2 over that is positive. Added to this positive 1 is a positive number. So f prime of x is positive on the rightmost interval. Now let's jump over to the leftmost interval. And let's see, what's the sign going to be? It's either positive or negative. Think of it this way. Take a value of x that's like way over here on the negative side, a really big negative number, and look at f prime of that x. It's 1 plus 2 divided by the cube root of 3x minus 3. So the 3x minus 3 would be a really big negative number. You take its cube root, that's a big number, divided by 2. The bigger and bigger x is in the negative direction, the smaller and smaller this reciprocal becomes. It's negative, but getting closer and closer to 0. So 1 plus that small number would be a positive number. So we would conclude that f prime is positive on this leftmost interval. What about the middle interval? Well, one thing you could do is just take a number, a really convenient number, like maybe x equals 0, that's between negative 5/3 and 1, and just plug that into f prime and see whether you get a positive or a negative. So let's do f prime of 0, and remember here's f prime, so that's 1 plus 2 over cube root of 3 times 0 minus 3. That's 1 plus 2 over the cube root of negative 3. The cube root of negative 3 is like negative 1.4 if you check that on a calculator. So 1 plus 2 over negative 1.4 would be 1 minus a number that's less than minus 1, and that's negative. So f prime of 0 is less than 0, which means we're negative on this interval. If you're in doubt, just take a calculator and work out f prime of 0. You'll see you get a negative number. So there we go. We figured out the sign of f prime on those 3 intervals. So our answer now is f increases on the interval from minus infinity to minus 5/3, and also on the interval from 1 to infinity, where f prime is positive. And f is going to decrease where f prime is negative on the interval from -5/3 to 1. And there's our answer. You see, we've come back to our function f. We've determined where it's increasing and decreasing. At this point, we're done with the derivative. The answer has nothing to do with the derivative. The derivative was just part of the process. We're done with this example, but just real quickly, I want to point out that if you graph this function f of x, this one, it would look like this. It would be increasing up to right there, then it would start decreasing, there'd be a cusp right there, and it would bounce back up. It's an interesting looking graph. Right here at -5/3, f prime of x is equal to 0, and right here at 1, f prime of 1 is undefined. So that's it for today. A quick summary. We've seen that where f prime of x is greater than 0, f is increasing, and where f prime of x is less than 0, f decreases. Another big point for today, a number c in the domain of a function f is called a critical point of f if f prime of c equals 0 or f prime of c is undefined, as in this picture. And those critical points, you're going to find that where a function switches from increase to decrease, it's going to happen at a critical point. And finally, we have this process of finding where a function increases and decreases. And it's important to get some practice with this. A little practical piece of advice. When you're working these problems, you're going to find, I think, that most critical points in practice, they tend to be the ones where the derivative is equal to 0. Like 90% of the time, the derivative will be 0. But every once in a while, you get a critical point where the derivative is undefined. So watch out for that. It's important to work some examples to have a full understanding. Just watching the lecture is not enough. Work those examples. Coming up next in lecture 31, we're going to examine a topic called local extrema, which is basically finding the hills and the valleys of a function. I'll see you then, and goodbye.